Hi, welcome back. This is lecture 22 in this course on Bayesian modeling. My name is Himanshu Yadav, and I'm going to introduce how to build a model in the Bayesian framework step by step, right? So we'll learn the whole workflow of building a Bayesian model, okay? And some of the steps that you have already covered in previous lectures, but in this lecture we'll see the whole workflow, that how to build a Bayesian model step by step. So let us begin. So the first thing you need to think of in while building a model is that what kind of outcome or what kind of data you're going to model, right? So basically you need some problem statement or some experiment, right? So let's say you are interested in modeling this phenomena. So you should have something that you want to model, right? That's the first thing you need. So let's say you want to model data from this experiment where participant sees a sentence on a screen. The key are rusty, for example, like this. They see a sentence on a screen and their task is to judge whether this sentence is acceptable or not. So acceptability judgment task. For example, you can think of other examples like let's say in a task participants are shown images one by one and their task is to judge whether this image is AI generated or not, right? So it could be any task. Okay. So they are going to make a judgment, yes or no. Okay. And what we are going to do, we are going to show them 100 sentences. Okay. And we are interested in measuring that how many times they gave a correct response. So how many correct responses. Okay. So we can call this variable number of correct responses and correct. So that's the variable, that's the outcome we are interested in. Okay. And that is something we want to model. Okay. So how do we build a model? Okay. So let us see. So now you know what kind of outcome you want to model, right? Now you can make assumptions, right? And basically model is just a set of assumptions, right? So now you can describe your model. Okay. So let's say this is your model. Okay. So the first thing the model would have is a likelihood assumption. So this is a step one, which is specify the model assumptions. Okay. I specify your model. Okay. How do I specify it? We specify two kind of assumptions. First, the likelihood assumption, which is this, that what is the underlying generative process behind the n correct, the outcome of this experiment. So what is the underlying generative process that produces n number of correct responses in this experiment, right? So let's say we assume that the underlying generative process is a binomial process, which is a reasonable assumption to make here. So we assume it comes from a binomial generative process with underlying probability theta in a particular trial. So theta is the probability of giving correct response, probability of correct response in any trial, in any particular trial. Okay. So that's your likelihood assumption. Now you need to make prior assumptions about theta. Okay. So what kind of prior assumption you can make about theta? What is theta? Theta is the probability of producing a correct response in a particular trial. So let's say the participant who is seeing these sentences is a native English speaker. Okay, the participant's mother tongue is English. So they are likely to make correct response in most of the sentences. Why they would have apparent difficulty in recognizing whether this is a correct sentence or not. Okay, but they can still make some mistakes sometimes, or they might be uncertain about the input. They might be uncertain about their knowledge of the sentence, right? Their linguistic knowledge. So there would be still some uncertainty. So, although most of the times they will produce a correct response, they would have a very high probability of producing a correct response, but there could still be some uncertainty around it. Okay. So, that is what we need to express. So, that is our prior assumption is going to be. Also, if you have some prior information based on previous experiments on the same task, let us say you have done the same task previously, right, and from that task you have estimated the underlying probability of producing correct response, then you can use that to specify your prior distribution for the current experiment. Okay. If that is not available, you need to make some reasonable prior assumption. Okay. So, what you can assume here is something like this. So, let us say theta comes from a beta distribution with shape parameters, let us say 90 and 10. And you can visualize in R how this distribution will look like. Okay. This distribution will look something like this, that average value would be at 0.9 and it is strictly between 0 and 1. Average value would be around 0.9 and most of the probability mass would be between 0.75 and 1. Okay. This is how the prior distribution of theta would look like. This is how the beta 90-10 looks like. Okay. All right. So, now we have set up our prior assumption and our likelihood assumption. So, this is your model. So, we have specified our model. So, this is step 1 in model building. What is step 2? Well, we actually conduct the experiment. Step 2 is to collect data, right. So, collect observed data. So, let us say and correct obs. This is the observed data in an experiment, right. So, number of correct responses observed in the experiment, and let us say this and correct obs is somewhere like, let us say 87 or something. Okay. So, this is your data. Okay. To make it shorten, you can also call it x obs. So, this is the observed number of correct responses in this data, okay, in this experiment. So, this is your data. Okay. Now, once you have data, now you can estimate the posterior distribution of theta. How do we do that? Posterior distribution of theta given the data x obs is given by likelihood function of theta given x obs prior distribution of theta divided by marginal likelihood. Okay. And there are different ways to calculate this posterior distribution. We have seen a couple of very simple straightforward ways, but there are much more sophisticated ways to do this, right. So, but our goal is to estimate this posterior distribution of theta, and let us say the estimated posterior distribution of theta is p hat theta x obs. We will always indicate estimated distribution using hat. So, we will write p hat rather than writing just p, because this means the true posterior distribution, this means the estimated posterior distribution, right. So, because you cannot exactly know what is this, because the method that you are going to use to estimate the posterior distribution is always going to be some approximation. So, that is why we write p hat. So, it is an estimate of true posterior distribution, right, given the data. So, if you have different data, you would have a different estimate of true posterior distribution, right. So, this is our estimated posterior distribution, right. So, that is a step 3. So, estimate the posterior distribution. So, there is one more step that we have missed here, which you have seen in the previous lectures, was this, that before even collecting any data, okay, before even collecting any data, you can do this step, let us call it a step 1.2 or something, that you can generate prior predictions. That you can generate prior predictions from the model and see whether your prior predictions look reasonable or not, and that is a check for whether your prior distributions are okay or not. Okay. And then you collect data, you estimate posterior distribution. Now, once you have posterior distribution, now you can generate posterior predictive data. Okay. How do we generate posterior predictive data? Well, draw a sample from the estimated posterior distribution and conditional on that sample, draw predictions from the likelihood function that you assumed, which was in our case binomial likelihood, conditional on theta star, which is a sample from the posterior. Okay. So, this is how we generate posterior predictive data. And in step 5, you can do PPC, posterior predictive checks. Okay. How do we do posterior predictive checks? That you compare posterior predictive data against observed data that you have used to train the model, okay, and see if they look similar, if they align with each other. If they look very different, that means your likelihood assumption is unreasonable. Okay. And then there is also step 6, and this is the most crucial step, which is model comparison. So, basically in this step you would do some theory testing or hypothesis testing or evaluate the predictive performance of your model. Okay. In this step you would employ some method, for example, let us say cross validation or Bayes factor. We will see them later on, you do not know them right now, but we will need to compare the model. So, model you have developed, let us call this model M1 against some model M2. Okay. So, let us say model M1 and M2 look like this. Let us say model M1 is like this, that the number of correct responses comes from binomial theta, where theta comes from beta 90-10, and model 2 tells you that number of correct responses comes from binomial theta. Okay. So, the likelihood is same, but the prior on theta is, let us say, beta 50-50. That means we think that the likely value of producing a correct response is 0.5 and there is uncertainty around it. Okay. So, these are competing prior assumptions while likelihood assumption is same. Now, given the data, you can compare which model performs better. Okay. And then we can claim that this is a better model, or more precisely this is a better assumption to make. Okay. So, under the assumption that theta is somewhere around 0.9, the model performs better. Okay. You can do much more sophisticated model comparison as well. Okay. But that is just to show you how it is done. Okay. Now, what is happening in all these steps? Okay. So, in the first step we specified the model assumptions, right. In the second step we generated prior predictions from the model. So, before even seeing any data, we are generating predictions from the model. Then you collect data. At this point, when you collect data, you can compare these prior predictions against observed data as well, right. So, that is also a very good check. And then once you have data, you can estimate the posterior distribution. This step is called parameter estimation, because you are estimating model parameters. This step is called parameter estimation. And then you generate posterior predictive data and you compare it against observed data. So, this is called posterior predictive checks. So, these are useful for checking whether our likelihood assumption is reasonable or not. And then step 6 is model evaluation. So, you evaluate the predictive performance of the model against some future data. Okay. So, this is model evaluation. So, these are the crucial steps in model comparison. So, this is prior predictive checks. By the way, prior predictive checks can also be used for an approach called region of practical equivalence. We will see that later on. and this is specifying the model. Okay. So, model assumptions, specifying the model assumptions. Okay. So, if you can master all these steps, that how to specify model assumptions, how to specify reasonable model assumptions, how to do prior predictive checks, how to estimate model parameters, how to do posterior predictive checks, and how to evaluate a model. Okay. So, these are how many? 1, 2, 3, 4, 5. These are 5 crucial steps in Bayesian model building. If you can master these 5 steps, okay, then you know how to do Bayesian modeling. Okay. So, this is it. So, this is the goal of this course, that you know how to implement each of these steps, even for more complex problems, even for more complex models, right. We will learn how to do all these steps. So, for example, things will get complicated when our model becomes more complex. It will get complicated to estimate model parameters. So, parameter estimation would require more complex algorithms. The model evaluation would also require more complex algorithms, right. But once we have mastered these 5 steps, you will be able to basically model anything in the Bayesian framework. Okay, and that's the goal of this course. But this is the workflow that you should keep in mind, and you should implement it every time. Even if you are working on a simpler problem, you should have this workflow in mind. That first you should clearly specify what are your likelihood assumptions and prior assumptions. Then you should check prior predictive distribution. Then you should estimate model parameters. Then you should do posterior predictive checks, and then you should evaluate your model against a competing model. Okay. So, that is the whole workflow. There are a couple other things that you will get some clarity later on. For example, in the parameter estimation process, you get a posterior distribution of the parameter, right. This posterior distribution is very informative. It tells you what are the likely values of your parameter. For example, in this case, let us say a posterior distribution comes out to be from 0.6 to let us say 0.9. It tells you that the likely value of theta, likely value of producing a correct response, is between 0.6 and 0.9, given the data and the prior assumptions, right. And you can calculate a so called 95% credible interval, okay, which will tell you that you can say with 95% certainty that the true value of this parameter theta lies between 0.6 and 0.9. We will come back to this point later, but I just want to show you that these are the inferences you can make about parameters given the posterior distribution, right. Also, given the posterior predictive data, so you can use these posterior predictions to say that this is what my model predicts for future data. Okay. So, given the current data, I have generated these posterior predictions, and you can then tell the community that these are the predictions of your model, and then they can test it. They can collect more data in their experiment, and they see whether their data aligns with your posterior predictive data, right. So, that would be a direct test. You can call it the confirmatory test of your theory. Okay. So, this is it in this lecture. This is how you can develop a whole workflow of Bayesian modeling. You can implement it in R. You know some of the steps. You can try it for a simple example. You know, for example, at this point, how to specify likelihood and prior assumptions, how to generate prior predictions, how to estimate posterior distribution using a simple method where you take a lot of values of a parameter and calculate its likelihood and prior density, and you multiply them to get posterior densities corresponding to each parameter value, and then you can sample from this vector of parameter values to get your posterior samples, and then use those posterior samples to generate posterior predictive data, right. You cannot do model comparison at this point because I haven't taught you, but you can at least practice these step up to step 5. Okay. So, all right, this is it in this lecture on model building in the Bayesian framework. So, this is a workflow that you should follow every time while even doing data analysis or while working on a model building problem or during model comparison as well, right. All right. So thank you very much. In the next lecture, we will see, we will talk about Bayesian learning. So what is Bayesian learning? You might have heard about this concept. So we will see how a Bayesian model learns iteratively. Okay. When you do, let's say, multiple repeated experiments, Bayesian model can learn from data every time and can keep updating its posterior distribution. Right. All right. Thank you very much. And we will meet in the next lecture to see Bayesian learning. All right. Thank you.